Hi, my name is Paul Haas, and this is my talk on advanced format string attacks.
Go, Paulie.
A little bit of background. Contents of this are going to be a little bit of background on me, an abstract of what format strings are, how you exploit them, a definition of sort of the way in which C functions are made vulnerable to it, context in terms of old, current, and new attacks. I'm going to show you my new techniques for exploiting them and actually go through a couple of demos before actually showing you a couple of full exploits, popping root shells without doing any work. Then I'm going to show you my tools, how I do it, finally leading to a conclusion, then Q&A. So I work for Redspin Incorporated as the lead web application security engineer. This talk isn't associated with that at all. It's just for fun and because I like doing some binary analysis type of stuff. I'm a former CTF champion here at DEFCON, so hopefully I know what I'm talking about. You guys will make a decision for me. And for those of you who don't play Mario Kart apparently, it's all about robot and tank on Rainbow Road. So the purpose of this talk is to take a vulnerable program like this, get a shell, without doing any of this. So a little bit of brief background. Format string attacks, for those who don't know, are a vulnerability in a type of C function, printf type functions that basically can lead to shellcode executed. Even though it's been sort of resolved, ignorance and vulnerabilities still exist. Otherwise, I wouldn't be talking about it. It's especially common in academic exercises, CTFs, a lot of legacy pen tests. The reason I brought this up is actually because one of our clients had this issue and I didn't feel like doing any additional work on it, so I created a tool to exploit it for me. This name of the talk is Advanced Format String Attacks, so I assume you know a little bit about what format string attacks actually do and how they work. Thankfully, the tools I'm going to be talking about don't require any knowledge. They're pretty much point and click, as you'll see. Brief history. Format string attacks have been around for about 20 years, sort of reaching the apex around 2000 for being popular, being really well known. The last format string attack that I've seen has been in 2010. So they still all are around, as you can see. The old technique used to be really kind of a pain to create. It required a long string of doing these manual popping using %x, %p in order to sort of get to your interesting data on the stack. Often when you want to actually create the exploit, you have to use a variety of other tools. Look for shellcode in your core after a seg fault. Basically, it's a lot of having to read the manual, consult the document, and then once you wrote it for one program, you couldn't take that work and then bring it anywhere else. So. The current has improved a little bit on this, but not much. It's still sort of the same technique. Some of the advances have been direct parameter access. So rather than having to pop, say, 10 things off the stack, you can just reference the 10th parameter directly. But again, you still needed to sort of use external tools to access, where you want to actually overwrite your code for. The technique that I've been working on basically utilizes information that, because you're dumping the stack, and the stack of most programs, C programs, has interesting information in it, you can use this information to basically leverage piece by piece of exploit, leading to the eventual compromise of the application. For example, most stacks contain data, code addresses, addresses that point to code, as well addresses to point to other information on the stack, such as data pointers or code pointers. And what's also interesting is that the string that we pass for a format string attack is also on the stack. So we can locate that as well as its offset. And with this information, we basically can locate the address of anything on the stack, which is useful, for example, if we find a code pointer that we want to overwrite on the stack, we can find out the address of that pointer and then overwrite it with our format string attack. So here's the vulnerable code that I've been using. Obviously, it's not going to work in secure environments, but you still see a lot of this, bits and pieces here and there. So, I wouldn't be expected. I would be pretty expected to see it in a couple of pen tests that I've been doing for legacy applications. Let's talk about a little bit about the exploit steps for my new method. I first dump the stack using an exploit string until I find that exploit string on the stack. I then find the address of that format string address on the stack. Then by finding the physical location and the pointer to that location, I basically can calculate the address of any other stack pointer or stack data that's present in my dump. This basically allows me, if I find any code pointers or return addresses, to say I can overwrite that address to point back to my shell code, which is also on the stack. One note with this is because I'm sort of leveraging multiple executions of a program to derive this information, it's really helpful to keep the format string length constant, because if you change it around, so do stack values and stack addresses. And since you need that information to be relatively constant, it helps to basically just keep the same format string length across all these different runs, as I'll show you. The first thing you have to do, stack dumps, two methods. One, you just dump the whole stack at once using a bunch of %Ps or %Xs. Second method is to execute a loop with incrementing values. In this case, I have here just a little bash script. I'll show you a demo of this that does it and makes it really convenient to show what's on the data or what's on the stack. You then take this stack information, which is based on %P or %X, is going to be code pointers, and you actually want to convert it to the string representation of that data. By doing that, you basically can find the actual string that's located through those pointers. And then by doing that, you can find the offset of that string from the stack dump. So right here I have a decently long one-liner for bash. This is basically running our vulnerable printf function. Let's see. So basically, this function, when you pass it a string, basically just prints it to the command line. And you can see it's actually vulnerable to a trivial format string attack, basically. Oops, sorry about that. So this one-liner basically is going to loop through the printf, sending incremental values on the stack in order to see what's there, basically. So what this is the offset that I'm passing. This happens to be the string that I'm passing to printf. This is what printf returns to me, a code or stack pointer. And this is actually what that resolves to in terms of a string. So scrolling up, let's see if I can find where I'm looking for. You see that at about offset 138, sort of divided between offset 137 to 139, we have %138 which happens to be what I passed on the command line to printf. So here we've used knowledge of the exploit to basically find our string at offset 130, 137, 138. So we use that in a future step to sort of help exploit the program. The next thing we have to do, format string address. Now that we have the physical location on the stack, we want to find the pointer to that string. Two ways to do this as well. A sequential loop as we did before, which will cause seg faults in the case of if the pointer at the given offset isn't actually a pointer but some data value, it's going to seg fault. Which might not be good in certain environments. For example, if, on a pen test, if there's aggressive IDS systems. The other way to do it, the more sneaky way, is given the stack dump, since we already have all that list, since we have a list of pointers already, we can parse that list for values that actually are on the stack, and then just obtain the offsets from those values only. This avoids seg faults, is a little bit more elegant, and allows us to basically dump all strings in just one run of the program, basically. So let me show you the first brute force method, because it's a little bit more easy to run on the command line. How's it going, guys?
Pretty good. Good. We're tied. Yeah.
Very good.
We do all the hard work.
So same thing, a loop here, basically. One-liner that's going to basically pass a bunch of things to the same printf function and try to get both the value as a pointer of the location as well as a string. So you can see here that, again, it's dumping offsets showing, for example, what's the value, the pointer value, as well as the string that that pointer resolves to. So going back up a little bit, let's see if we can find it. So at offset 38, pointer that ends with 608 actually references itself, telling us that that pointer value actually resolves to our pass argument. This is the second step of the attack, basically. So given this offset that we found in the first stack dump and the address that we found in the second, we basically have a method to allow arbitrary win on the stack. We know that since offset 100 is at, for example, stack pointer BFFFF 100, and we know that a pointer is 4 bytes, we know, for example, that offset 1 is going to be minus 400 values from that offset, basically. So we have a return address at offset 10. We can calculate the return or the stack offset of that, and then when we're attempting our exploit, we don't have to get, for example, detours or program link table or some other overwrite location. We can just overwrite this location on the stack, which we've already found from a previous step. Even though it's possible, for example, in advanced format string attacks to sort of extract this information, we want to be sort of lazy and just have, this operations from previous steps do our work for us. Two methods to do this as well. If we know what a return address looks like, they're pretty common on most, Linux systems. We can use those. Or we can also guess them using sort of an algorithm that matches values that are close to each other that aren't data and aren't strings. Or we can also be lazy and just brute force everything on the stack until our exploit succeeds, basically, which is a lot easier to do, basically. Some issues with this new technique. As I mentioned, if we change the length of our format string, it's basically in effect addresses on the stack. Since our format string basically, as it grows, so do stack values grow in addition to it. The easy way to resolve this is basically to keep all format strings, during the technique the same size. Just pad them with, null characters or useless characters, so that when we actually attempt our exploit and append shellcode to the format string, that will happen to be the same length as all our previous executions of the program. The result of this is, given 2 executions of a program, 1 to dump the stack, and 2, if you're being really clever and just dumping all the string addresses, you basically can get all the information you need to exploit that function, basically. No brute forcing, just a little bit of math. It's also nice because the way this current technique works, you can shrink the length of the format string so that you can fit both the format string and the shellcode in, say, less than 100 bytes, which is usually pretty, reasonable for, any user input field, basically. However, if you don't brute force the override address, or if you don't do some math, you still have to derive it from some other source, such as, a core dump or, a known location like a program link table or the detours. So demo is the good heart of the talk. The first tool, which should be on your DEFCON CD, is a proof of concept tool in Python. I have instructions for running on Backtrack 4. Basically, it's a nice little suite for demonstrating sort of the way the attack works. Multiple options about where you want to overwrite, where you want to put your shell code. Again, since the proof of concept is missing some useful things, but those can be really easily added, hopefully by anyone who has an understanding of this talk. So I'll demo the tool right now. Taking our same printf function that's we know to be vulnerable to format string attack, and just for the sake of vulnerability sync, we'll make it ownable and then executable by root, so anyone will inherit those permissions. I have a dummy account right now that has limited permissions. Obviously, I want to exploit this printf function, gain root access. I don't want to actually have to do it to myself, so I'm going to basically use my tool. So that's a little hard to read, but basically it's just going over the options about where you want the exploit to override and where you want the shellcode to be. But the nice thing is you don't really have to read any of that because you can just click it with the binary and you're in, basically. So, and the nice thing is this technique works on any similar exploiting type of vulnerability, basically. The question was, would this work on a syslog thing where the output's going somewhere else? This attack basically works as long as you can read the output from former vulnerabilities and use those in new vulnerabilities, it's going to work, basically. The next code I developed, especially for DEFCON, designed to be as loud and invasive as possible, has been completely automated, so I sort of removed that reference to having to get an overwrite location. I'm using basically brute forcing through the stack. Ported both to Python and Ruby. It's under 100 lines of code, so hopefully if I have time, I'll go through it right now and talk about it a little bit. Basically, it does the same thing except using a brute force attack. So let me show you that as well. So again, same printf function. Same dummy user. Different binary. So again, you just pass it the vulnerable function as a parameter, and you get a root shell. So even though you can't see it right now, for example, if I exit, you see right now it's actually brute forcing a bunch of spaces, trying to go through all the stack values until it finds it. As long as it's there somewhere, you're going to get in. So if that's all that matters, you can be invasive as possible. I'll show the Ruby version. Does the same thing, but for those who like Ruby better, you also can get a shell. Finally, the meat of this talk. If you're going to have this sweet program, you might as well port it where someone can use it. In this case, I've decided to move it to Metasploit, add it for the capability for remote exploit. The usefulness of this is that you can use an arbitrary payload, anything from Metasploit. The code is there in Metasploit in a known location, so if you want to extend, your functions for another vulnerability, you can just use Metasploit for it. And for this, I created, a sample vulnerable server that basically does the same thing, as our printf vulnerable function, except, through a TCP connection. So let me demo that right now. So I'm not gonna go through this too much, but basically it opens a port on 4546. Forks a process for for connections, and then it basically sends SN printf vulnerability right here back to that socket that you connected to. So let me make this and go ahead and run it. So this is running on my VMware. I'm going to try to exploit it from my local Ubuntu machine. Metasploit's taking a while, don't worry. That's correct. This assumes, this is for kind of legacy environments where a lot of those protections are non-existent. So while Metasploit's loading right now, I'll go ahead and just show you that it indeed basically just, by piping something through netcat to that server and through that port, it basically does the same thing, gives sort of this, data disclosure. How's it going, guys? Very good. Oh, these are my coworkers from Redspin, so they're here to play Mario Kart with me, basically. They don't have any relation to the talk whatsoever. Okay, there we go. So right now I'm going to load my custom Metasploit module. Show payloads. Let's see. What do I want to exploit today? Linux x86. I'm going to go just use a reverse TCP bind shell. See are my options for this. Looks like it accepts remote host, remote port, local host. So I'm going to go ahead and set those. .130 in this case is my VMware machine. And 58.1 is my local machine. And hopefully this will work. So the nice thing is, since we're brute forcing the stack, any return address on that stack is going to give us a shell. In this case, it happens to be six overwrite return addresses on the other program. So now you can share a shell with your friends and family if you would so choose to. And we can verify that by, listing the sessions and then sending a command to them. So you can see that I compromised this application 6 times and got a root access on all of them. Looks like I'm doing really well on time, so I'm going to go through my brute forcing code in Python. Hopefully you guys will get something out of it. It's only about 100 lines of code, 4 steps. So first thing I do basically is just, standard, wrong one. I basically just have, initialization, setting up my variables, defining some functions. Second step, I basically go through that stack dump process as I showed you before. I use this data basically to find, an offset address of the found format string. The next step after that basically is, I'm looking for the address of that format string. So basically, I run another loop to find that address. And finally, when I'm actually exploiting, all I do is create the exploit string and then run through this brute forcing technique. So 68 lines of code, hopefully pretty extendable, used on a variety of, similar instances. So hopefully you guys will find some use out of it. In conclusion, format string output gives you everything you need to actually go from discovery to compromise. It could be completely automated as I've shown. They have been easy to fix. Now they're easy to exploit. For those who are interested in finding some of them, a good suggestion, Google Code. A good dork to look for this type of thing is shown there. This basically look for a C language printf type function that doesn't begin with something like a constant, something that doesn't begin with something like stdin or stderr, or something that begins with a parenthesis. So hopefully something that is actually using a buffer or a non command line, or something that uses something that the user has provided in terms of a buffer, basically. So thanks. Hopefully the tools that aren't on your CD will be put on Redspin and DEFCON shortly, Monday, I'm hoping. I'm hoping that the Metasploit module will also be there as soon as I talk to those responsible for weird auto-format string stuff. You can contact me. Otherwise, shouts to all the people at Shellfish and my people playing Mario Kart with me. Questions, Mario Kart, hopefully, looks like we have plenty of time, but hopefully we'll be in another room if you don't have any right now. So. Can you repeat that one more time, please?
If this your concept, does it assume that whatever printf function implements direct parameter access? That has some sort of
So the question was, does my proof of concept assume that there's direct parameter access to exploit it? And the answer is yes. So I basically assume that most modern versions or most versions that I've seen have used that direct parameter access. Again, the technique can still be modified. You just have to do it yourself.
How hard do you think it would be to modify this to actually work with like address-space layout randomization, for example?
I don't know. I think it would be a good exercise, but I wouldn't be surprised if you could do it. Because if you dump the stack enough times, you're still going to have a general idea about where stuff is relative to everything else on the stack. So you still could do some sort of permutation attacks, and if you're brute forcing anyway, it's only a matter of time. Okay, guys, thanks a whole bunch.